Okay, in this video, I'm going to explain what stationary phase argument means. This phrase first appears in lecture 1 here when I explain Dirac's proposal and how that is modified and Feynman's path integral statement evolves from that. There, I give some mathematical argument here where I have used stationary phase argument, which basically says that in the h bar going to 0 limit, the quantum contributions all are coming from only classical paths. So that is the statement. Now let's look at the calculation where this is happening. It's in the calculation of the path integral, say. One can use the same argument here also, but let me consider because ultimately this statement is equivalent to the Feynman path integral, which has been explained in lecture 1. So I'm going to explain what is stationary phase argument by considering this calculation of this quantity. So let's have a look what we are trying to calculate. This is a phase. The integrand is a phase, and then action is a functional of paths. We have already defined the paths given by the initial and final conditions. If you have x and t, this is initial point and final point, and then you have different paths. For each path, you calculate the value of the action. When you change the path, the value of the action changes. You could also think of that function space, that cartoon that I had drawn in lecture 1, where I explained what the function space is, where when each point represents an allowed path with the particular boundary conditions. And then action is an ordinary function in that space. Given any point, you calculate the action and you get a real number. And then this integral, this path integral, is an ordinary integration in that space. So you are basically integrating over this space, and the integrand is this phase. Okay, now let me call this exponent the theta, which is s over h bar. And then therefore this would be cosine theta plus I sine theta. That is the integrand. Okay, this is what the calculation is, because theta is a functional of paths. When you change the paths, theta changes, and you are calculating this integration of this quantity. Now first let's understand what h bar going to 0 limit means. What is the meaning of h bar going to 0 limit? H bar is a fixed number in nature, so you cannot send it to 0. What you are actually doing is that you are considering action divided by h bar to be very large. Now what it means is that the value of the action in units of h bar is very large. So this you can achieve in various ways. I mean, you change the action, you change the system. We are changing the system, and therefore value of action is changing. So you are changing the system in such a way that a typical value. So while changing the system, let's fix our notions here. We are not changing the space of functions. So that space of functions remains the same. That means we are considering the same set of paths. Okay, we are considering the same set of paths, but the value of the action for a given path or a given point here, that changes because you are changing the system. So we standardize first the all possible paths. That's like fixing a coordinate system, and then you are calculating the function in that using those coordinates, and then only you can compare the values of the action, values of the function. So here the function is action. So you are changing the system in such a way that the value of action is increasing in units of h bar for the same paths. One simple way of doing it is to keep the functional form of the action same, but change the parameters that are sitting in the action. For example, if it is a particle, action can be quite complicated. This what I'm discussing here is very general. Okay, it can be very complicated action. It could be a simple action as well, where it describes a free particle, say of mass m. Then the mass parameter can be cranked up to increase the value of action, and then that would make s bar h bar to be very large. So why do we not talk about s going to infinity or s becoming very large? That is because that you can make the value of action very large in various ways, by changing parameters, by changing the system altogether. What we are going to discuss here, the very behavior that we are going to discuss in the h bar going to the zero limit, that it picks classical paths or the stationary fixed phase argument, that doesn't depend on the details of the action. Whichever way you change the action, all that is important is the value of the action divided by h bar is very large. So that is why it is easier to talk in terms of h bar going to zero limit. It's a formal way of talking, and it's a way of talking by the theoretical physicists. Okay, so this is what the meaning of this statement is. This is what we are going to follow. Now let's have a look at this quantity. I said that this is cosine theta plus I sine theta. Let's look at cosine theta. Cosine theta versus theta. So this is cosine theta versus theta. It doesn't matter cosine theta or sine theta, they are just a phase difference, and we know that it is oscillatory like this. So when we change the paths, we are changing theta. Theta is s over h bar. This is theta, and this is dimensionless. And therefore, we can talk about its value, whether it's order 1, whether it's very small or large, because it is dimensionless. So when we change the paths from one to the other, then we can look at the change in theta. And so this corresponds to a delta theta. Because we have changed the points, it will give you a change in theta. So that is the delta theta, which is, say, from here to here. This is delta theta. Now we know that in our integration, if we do this integration, we can look at it in various ways, like you are slicing it and then take the usual limit definition of integral, etc. It's an easy thing to get convinced that if we have equal contribution in the positive and in the negative direction, then the net result will be 0. So the delta theta will be 0 for this. However, when you take a generic difference, generic variation of the path, delta theta will be generic, and there will all this kind of cancellation will not always take place. You may be, your delta theta may be ending here, in which case you have a net contribution, which is this. So that would be the result of doing that much of the integral, of doing a calculation where you are varying the path that much. Okay, so if you're when you change the path gradually in the space of paths, okay, and theta changes gradually, yeah, then this is a well-defined calculation. You can do that, right? It is same as calculating, you know, integral d theta cosine theta, though here theta is a function of x, so you are actually integrating over x, not directly over theta. Now, what happens in the h bar going to 0 limit? In the h bar going to 0 limit, for the same different paths, you take this path and this path. Earlier, when you take h bar to be finite, for these two paths, you had a delta theta, which was like this, or something like this, right? Either it was cancelling, giving 0, or it was giving some non-zero result. However, when h bar goes to 0, the same two paths will differ by a very large delta theta. A very large delta theta would mean what? That would mean that so let me now okay, so the correspondingly you will have, since it's very large delta theta, I am squeezing in this picture visually, it's actually a very large number. This is delta theta. How do you know that it is large number? The way to know, when you plot cosine theta, you will be having very large number of oscillations. When it goes to a very large number of oscillations, then most of them will cancel with each other, and only the part that is not cancelled will remain as a result of the integration. However, this is called so when h bar is very small, I mean delta theta tends to become very large for the ordinary variation of the path. That would be the situation. But when you send h bar to 0 absolutely, then delta theta is basically going to infinity. Then when h bar is very small, delta theta is very large, then this integrand is oscillating very rapidly for the same variation of the paths, and this is sometimes called wildly oscillatory. Integrand or integral. So these wildly oscillatory integrals are difficult to calculate because of the following reason. Even if the oscillation is large, but we still can count how many complete oscillations have gone and how much is the remaining part, that would give the result. Still a well-defined question to ask. But when you say h bar going to 0, which means that there are this number of repetitions going to infinity, then there is no way to figure out that what is this amount. It is an ill-defined question because there are infinite number of oscillations. So this is the problem of highly oscillatory integrals. Question is that how do we sort out this problem? Now there is an intuitive proposal which is not mathematically rigorous. That intuitive proposal is the stationary phase argument, will be coming out as the stationary phase argument. But for the mathematically rigorous justification of that is a separate issue that I will not discuss here. That is the analytic continuation, which is discussed in lecture 3 when this weak rotation or Euclideanization or I epsilon prescription was done. These are basically the mathematically rigorous measure to make those intuitive expectation of stationary phase argument really true. Okay, so that I will not discuss. I'll discuss what is the stationary phase argument. So here is how the argument goes. Let me consider, instead of this quantity, a little bit more general quantity, more general integral. Let me write it here, which is given by integral dx some functional fx and then e to the power I by h bar sx. Okay, it is analogous to an integral in one dimension. I think that will be easier to understand. So right now what I'm talking, what I'm explaining, it doesn't really rely on the fact that we are on the function space. Function space, we will use the same argument which applies in the function space integral. That just makes it more formal because we are doing the integration in an infinite dimensional space. but the basic idea can be demonstrated even in one dimension. So that's let me do that. So we have an integral dx function fx e to the power I sx over h bar. So sx and fx are ordinary functions. They are not functionals, and x is just a real line. So in this case, we know our idea of doing the calculation in absence of this, in absence of the phase, we would do the method of integration is that we basically calculate the area under the curve. So what it means is that we take a infinitesimal differential element over which fx is considered to be constant, and that's why we write fx dx. Yeah, that is the area under the curve. However, when the phase is present, then this function, the integrand, will be modulated by cosine theta and sine theta coming from this phase. So it will be cosine theta x, fx, and dx. Okay. So when under the variation of x, when theta x changes by a finite amount, then this is as easy as doing this integral. However, in the h bar going to 0 limit, in the h bar going to 0 limit, what is happening is that, let me draw another cartoon here. So let me enlarge. This is dx. And the function fx is almost constant over this range. However, because h bar is going to is tending to 0, the variation of theta is very large within this differential line element. The variation of theta is very large, and therefore it will go through an infinite number of oscillations. So this will be multiplied by an infinite oscillation like this. And when you multiply a constant with this infinite oscillation, which has equal contribution, now we are assuming that the number of times it contributes positively is same as the number of times it contributes negatively. This is an assumption. This cannot be rigorously established, because the reason why this integral is ill-defined is that there are infinite oscillation, and we don't know exactly how many positive contributions which are cancelling how many negative contributions, and what is the remaining amount. So stationary phase argument says that let us assume that this cancels this exactly, and the result is therefore 0, because it is multiplying a constant, and therefore this result will be 0. If we do the integration, the net area under this constant times this variation will be 0. That is the stationary phase argument. So stationary phase argument would therefore say that integral dx fx e to the power I by h bar sx will go to 0 in the limit h bar going to 0. Okay, that's basically the argument. And as I said, that it is not a rigorous argument. It is we are imagining this is how it is operating. To make it rigorous, we have to do the analytic continuation, and we have to make sure that a more mathematically more rigorous procedure would actually give the same result. And that's the topic of Euclideanization or I epsilon prescription, that this has to be discussed separately. It has been discussed in lecture 3. Now, when we do this, and there is one assumption. The assumption is is this large fluctuation of theta within a small length element. This is not always true because the action can have extrema. When the action has extrema, it basically does not change. So in that case, this action, if the action has an extrema, then it will be constant over dx, and therefore the result will not be cancelling, and the result will not be zero. So if I go back to a cartoon of let me not do the cartoon, let me just do it in one dimension. So if you're integrating against x, fx e to the power I by h bar sx. So let me first integrate. Let me first draw the picture of sx. So sx would have a bunch of, you know, extrema. At the extrema, the action at any other point, at any ordinary point here, for the dx, there is a variation of s, and because of this variation, s by h bar goes to infinity, delta s by h bar. However, at this point, because delta s is 0, because it is an extremum, this is not true anymore, and therefore this contribution will not be cancelled, and if it is not cancelled, it will remain. So as we send h bar to, as we tune h bar to more and more close to 0, all the other path contributions are going to 0 more and more accurately, and only the contribution at the extrema will remain. The entire integral will be localized at the extrema of the angle, okay, or the phase. So according to that, then this is not a 0. It actually, what happens is the following. This actually goes to take summation over all the extrema, fx e to the power I by h bar sx, where x, so x0 equals extrema. That would be the result. And since it's the extremum of the action, that corresponds to the classical value, classical configuration. In the context of this function space, this x0 is actually a path, x0 of t, a path, and these are the paths where the action is extremized, and therefore they are classical paths. So therefore, not only this integration, but a more general integration where you have a functional sitting in addition to the path integral phase will give in the h bar going to 0 limit, classical paths. Okay, and that is precisely what is happening here in this calculation. This expression is equivalent to the path integral, and but in the because these intermediate points are integrated over. But when you take the h bar going to 0 limit, it's only the integration is local. All this integration is localized only on the only one classical path, okay, one or few classical paths, and then this phase or these integrations are all gone, only the phases remain, and the phases are calculated on for the values of for the values which correspond to the classical paths, and those are the x tildes. Yeah, that is how this goes to this in the H bar going to 0 limit.